Three more examples of a binomial probability with this in the same context. We've got 5 wind turbines, and we are assuming, making a big assumption, that the working or failure of uh, any of the wind turbines is independent of the others. And that, in this situation, I would say that's an approximation and not a golden thing. If we're talking like die rolling, then it's much more likely to be really close. Okay. Okay, so we did the probability of exactly 4 were working. Now I've changed it to 3. It's going to look very, very similar. But again, the main thing is not to make the mistake that it's the probability that exactly these 3 are working and these 2 are failing, although that will be part of the calculation. So the first thing, now we're going to do it right from the start. The first thing is simply you need to say how many ways can we choose which ones are the ones that are working and which ones are the ones that are failing. And that's exactly a binomial coefficient or a choose coefficient, exactly what combinations, whatever you want to say. We're going to say of these 5 slots, maybe we want to describe what's the probability that this one is working and this one's working and this one's working and this one's failing, this one's failing. So notice it's the number of ways we can take 5 slots and make a word with 3 W's and 2 F's. That's another interpretation of the choose coefficients. It's a anagram problem or distinguishable permutations problem with 2 letters, 2 different kinds of letters. Okay, so we're going to take the probability of this specific thing happening, 3 specific ones working and 2 specific ones failing, and then we're going to add that to all the different ways it could happen depending on exactly which ones work and which ones fail. Or another way to say that is we're going to multiply it by 5c3. So the 5c3 is a combinatorial factor, and then that's going to be multiplied by the specific answer to the specific question, which is a particular 3 are working or failing. It's a little easier sometimes to say, well, okay, let's think about that with the first 3 working and the second and the last 2 failing. But that's going to be assuming these are identical, which is another really important. These are identical, independent successes or failures. That's what binomial probability is about. Assuming they're identical, we're just going to look at, well, what's the probability that the first 3 specifically work? That's 0.9 to the 3, and the last 2 fail. That's 0.1 squared. So we repeatedly, over and over and over again, use the fundamental thing about independence, which is that independent probabilities multiply. Okay, and now 5c3 is 5 times 4. Well, it's the same thing as 5c2. I'm going to calculate it as a 5c2. So that's 2 numbers over 2 numbers. That's going to be 10. Okay, so the whole thing is going to be 10 times 0.9 cubed times 0.1 squared. And if you calculate that out, it's 7.3%. Now we're getting fairly unlikely, which is intuitive. There should be some intuition to this here. It shouldn't be ridiculously counterintuitive. Again, if we had a field of 100, we'd expect around 90 to be working. If we have a field of 5, we expect 4.5 sort of to be working. 3 is unlucky. That's a bad situation, and it's somewhat unlikely. But we're not going to say, oh my gosh, this is I'd never expect to see this. Okay. Um, so again, so let me. I think we're at a point where I can say exactly what situations does binomial apply to. We have independent, some sort of known number of independent identical things, so like n total independent identical trials of something. And then the question we ask, there's various questions we could ask, but the specific question is we're asking what's the probability that we get our successes exactly, and we're going to change that in a second, exactly our successes out of, and a very popular way to say that is out of n trials. There's a lot of other terminology we could put on this, and we would do that in like a stats class, but the probability of exactly our successes out of n trials, but I don't care which ones are the successes and which ones are the failures. I just am counting how many successes, okay? And that is NCR times the probability of each one succeeding, let's say probability of success, to the R, times the probability of failure to the n minus R. And notice that that's really, really like how these coefficients show up in a binomial. in the binomial expansion. The algebraic setting, they exactly show up as NCR times something to the R, something to the n minus R. So that's why it's really tightly tied to binomials. And you don't have to have seen that algebra, but it's a nice reinforcement. And the other thing to note is that we could just say little p is the probability of success. That's of each individual trial. Then the probability of failure, sometimes it's nice to sort of emphasize the symmetry here and just use another small letter like letter Q. But you know what? That's always going to be 1 minus p. So we're also using a complement principle here just a little bit. And we're going to use a complement principle again in a second. Okay. So you often see it written out in that way. NCR times P to the R times Q to the n minus R. And that's the binomial probability formula. So if you wanted a formula, there you go. Okay, so two more examples, taking it a little further. What about the probability that at least 3 turbines work? Because often you want this. You want to figure out, look, I'm going to be happy if at least 3 work. If I look, the exactly was a little strange in that regard. I don't care so much if I ask, if somebody goes to ask me, hey, are 4 of them working? And I say, oh, no. And the reason I say no is because 5 of them are working. They might be like, well, that's better. That's great. I'm fine with that. I really meant at least 4 are working, or at least, let's do at least 3 are working. So this is, am I in a situation where at least sort of the majority of these 5 wind turbines are working? Okay, well, the most straightforward way to do it, my black is running out here, I'll change to red just to be more vibrant, is to just divide it into exactlies. The probability, this is really the probability that exactly 3 are working, plus the probability that exactly 4 are working, plus the probability that exactly 5 are working. And there's other ways to do it, and I'll show you an elaboration in the last problem. But this is the most straightforward way to do it. And luckily, I picked one where we actually have all of those numbers in hand. The exactly 3% was 7.3%. The exactly 4 was in the previous video, which was 32.8%. And exactly 5, that's all of them working, that's 59%. And I think if you don't round it too much at the start, what it comes out to be 99.14%. Really, it's quite likely that the majority of them are going to be working because they're so good. And again, because I'm assuming that their failures or successes are totally independent of each other. And that's where this kind of thing gets you'd only regard this as a first approximation in that kind of case. If these were like this is like rolling a 10-sided die, and this is the probability that at least 3 of them gets either a 9 or a 10, then, or sorry, no, it gets a 1 through 9, then this would be right on the money. Okay, one last one in that same vein. What about the probability that at most 4 work? So we're now saying, well, let's be a little pessimistic. What's the probability that at most 4 of them are working? So we could do it in this way, similar to this way. We could say it's a probability that that exactly 0 are working, or exactly 1, or exactly 2, or exactly 3, or exactly 4. Those are mutually exclusive possibilities, and I could just add the probabilities. But you know what? The complement principle is really good here. Always think about that with at least at most. Think about the complement principle. We could have used it here, but it wouldn't have simplified things too much. Although it wouldn't have been a bad way. Here, if it's not the case that at most 4 of them are working, this is a very inclusive statement. There's only one way that can fail. It's all 5 are working. So we're really just looking at what's the probability that we're not at full strength. And the logic of that can be a little tricky sometimes, of figuring exactly what the right negation is. Okay, well that's easy, because that's 1 minus the 59% that we got in the last video, and that's 41%. So always be prepared to use either cases and addition, or sometimes you're going to reduce your work a lot by looking at the complement principle. So it was still based on this formula to get these individual numbers, but then also using our fundamental probability principles. All right, that's all the examples I want to do for these videos.